Good morning, Mr. Simeon. My partner and I, Dafen, are going to present our paper about skin cancer detection. Next. Before we discuss our paper, we must know the background first. Skin cancer is one of major public health concern globally, often triggered by excessive exposure to UV radiation. It is estimated that in 2022, there are about 330,000 cases of melanoma alone were diagnosed globally. And from those cases, almost 60,000 people died. Next. And so we want to provide we want to offer a solution which which is to develop an effective system capable of accurately detecting and diagnosing skin cancer by using artificial intelligence and deep learning. This is the workflow of our paper. The first one would be data acquisition, then sampling data. Then we will be training our model, pre-processing, feature extraction, classification, testing, and comparing. Based on the literature review that we analyzed and gathered, the majority of the paper uses CNN or convolutional neural network, which is basically a regularized type of feed-forward neural network that learns feature engineering by itself via filters or kernel optimization. There are a lot of there are different types of model that were used in the paper that we studied, such as Inception, VGG, and SVM. We concluded that TrustNet 50 is the most suitable for our topic. The metrics that we are going to use in our study is the first one is accuracy, which refers to how accurate the library can identify different types of skin cancer. The second one is precision, which refers to how often a model correctly predicts the positive class. The last one is recall, which refers to how often a model identifies positive instance from all the actual positive samples in the dataset. From our literature review, the most used dataset are ISIC and PH2 dataset. ISIC, which shorthand for International Skin Imaging Collaboration, is a leading repository for researchers in machine learning for medical image analysis, while PH2 dataset is a dermoscopic image database that has been developed for research and benchmarking purposes. The models that we are going to use in our study is MobileNet V2, Inception V3, ResNet 50, and DenseNet 121. MobileNet V2 is one of CNN architecture specifically engineered for mobile and embedded devices. Its core are depthwise separable convolution, which break down traditional convolutional operation into separate depthwise. This means that it will fully connected layers at the network end for high-level reasoning, and with its efficiency and accuracy, it can be one of the most versatile solutions for various computer vision tasks. The second model that we're going to use is Inception V3, which is another CNN architecture that uses 48 layers. This module within Inception V3 comprises a set of parallel convolutional branches that includes 1 times 1, 3 times 3, and 5 times 5 times 5 convolution. Through this multi-scale feature extraction, Inception V3 can discern patterns and structure across different levels of abstraction. The third model that we are going to use is ResNet 50. This architecture uses 50 layers deep structure that introduce residual connection that alleviate the vanishing gradient problems, allowing for more effective training of deep networks. ResNet 50 deep representation learning capabilities enable it to capture intricate features from images, making it suitable for tasks such as image classification, object detection, and feature extraction. The last model that we are going to use in our study is DenseNet 121. It's another architecture that uses 121 layers. that efficiently captures intricate patterns in the data, promoting information flow and gradient propagation. This leads to enhanced model training speed and robustness, ideal for tasks like image classification and object detection. This means that it can result in state-of-the-art performance across various computer vision tasks with fewer parameters compared to traditional CNNs.
Okay, moving on. I'm going to explain to you the code of this project. Each code models have the same code except from the construction model part. Okay. Firstly, we are mounting and installing a connection to Google Drive. In our Google Drive, the training and testing dataset are stored. There's roughly 2,000 datasets in the form of image. Secondly, we are going to install Augmenter. Augmenter is going to help the model to improve its overall performance. Okay. Next, we are importing relevant libraries for our project. There are tons of libraries we use in our project. The important libraries are TensorFlow, Glob, and Augmenter. Next, in this step, we are setting the type of connection used for running the code. We are using the GPU T4 type. The reason behind it is so the code can run a lot faster. Next, in this next step, we are defining variables we use in the code. We define a fixed batch set size of 32, image width and height of 224, and random seed number of 123. Okay, next, in this next step, we are determining the files used for training, validation, and testing. The training dataset and testing dataset variable are used to store the path of data in Google Drive. The training process variable is used to set the files used for training. The validation process variable is used to set the files used for validation, and the testing process is used to store the testing files. Next, in this step, we are checking the training dataset's image. We are checking whether or not the datasets are retrieved correctly from the Google Drive. For each classwork, we only check the first data in the list. Next, in this step, we are auto-tuning the training and validation datasets. Auto-tuning is used to help improving machine learning algorithms. It also checks whether the performance can bottleneck in the dataset side or not. Okay, in this step, we are augmenting the dataset. The augmented data will be stored in Google Drive. It will be placed in the augmented results folder. Okay, in this step, we are checking the augmented data sets. The total of the data of each class is printed, and the total is also shown in the form of a diagram. Okay. In this step, we are setting the training and validation files and testing files. The difference from the previous step is the datasets collected is from the augmented results folder. Okay. Finally, in this last step, we are showing the result of each of the model. The metric used in this project are precision, accuracy, and recall. This next, we are going to explain the result to you. Okay, with the Inception P3 model, the model reached an accuracy of 19 a precision of 31%, and a recall value of 53%. This is the table for the accuracy of loss of the Inception V3 model. Okay, next is the MobileNet V2 model. With the MobileNet V2 model, we achieve an accuracy of 22%, a precision of 19%, and a recall value of 99%. This is the table for the accuracy and loss of MobileNet V2 model. Next is the DenseNet 1-to-1 model. With this model, the model achieved 37% of accuracy, a precision value of 70%, and a recall value of 100%. Sorry. This is the table for the accuracy and loss of the DenseNet 1-to-1 model. Okay. Next is the ResNet 50 model. With the ResNet 50 model, we achieve an accuracy of 47%, a precision value of 93%, and a recall value of 89%. This is the table of accuracy and loss for the ResNet 51 model. Okay. Thank you for listening, and see you next time.